So what we've just seen in defining these 6 categories of engineering materials based on structural and electronic considerations is that in each case, either through a atomic level structural issue, the bonding between individual atoms, or in the case of the chairs, the microscopic architecture of the fiber reinforced composite, we see an underlying principle that is going to be a mantra for material science throughout these 10 things, and that is structure leads to properties. That's the underlying concept that informs all of material science, really. A structural issue, either on the atomic or microscopic level, that leads to our understanding of the nature of the material on the macroscopic or engineering level. So we're now going to look at a short, detailed lecture in which I discuss how the bonding curves, both the bonding force and bonding energy curves that we recall from freshman chemistry, lead us to an understanding of one of the most important of the mechanical properties of engineering materials. And we'll look specifically at the case of the elastic modulus or stiffness of the material. We'll come back to this in more detail in a later segment in another thing. But for now, we want to use this short lecture as our first formal example of how structure leads to properties. So now let's step back and talk in a little more detail about some concepts that we raised early on in our discussion of the stress-strain curve. And this particular sketch is one that I feel is, quite frankly, one of the most important in the course, and so I want to really highlight that and emphasize that this is one of the really seminal examples of this point we've made from the beginning in this course on engineered materials, that that fundamental underlying tenet of material science is that structure leads to properties. And what better example is that early concept of atomic bonding leading to this now very fundamental, one of our most fundamental mechanical properties, the elastic modulus or stiffness. So if we go back to that discussion of interatomic bonding, we're reminded of how the bonding force curve was the simple first derivative of the bonding energy curve. And we had that neutral axis, which we've circled here. On the force curve, which corresponded to that equilibrium interatomic separation distance, the bond length between any two adjacent atoms. So again, it could be 2 carbon atoms in a polymer. It could be 2 aluminum atoms in an aluminum alloy. Could be distance between an aluminum and oxygen ion in the aluminum oxide. In whatever case, that interatomic distance then is going to change slightly in our stress-strain experiment. So when we have this stress-strain tensile test specimen, we're in a position to effectively, down on the atomic scale, we're just trying to pull atoms apart. And of course, in the initial going, we're just simply increasing that bond length by a very small fraction. And so, even though this is a highly curved plot, this bonding force curve, again, we emphasized when we were talking about this early on in our discussion of atomic bonding, reviewing those basic chemistry principles that we'd likely seen before, that the tangent at this point is a nearly straight line. So that explains why the overall load elongation curve is straight. Again, it's just a macroscopic scale manifestation of that interatomic bonding, that local atomic structure that we introduced in that very early lesson And then when we normalize that data, the load versus elongation by sample geometry, then we get the general behavior of the material of stress versus strain. And so then we get this general parameter of the elastic modulus, which again, in terms of just practical mechanical performance of the material, that relates to the stiffness of that component in the overall engineering design.